Thank you. So we've been hearing a lot about Hopf algebras and tensor categories, different types, semi-simple, non-semi-simple. I'm mostly interested in the non-semi-simple Hopf algebras today, or the non-semi-simple tensor categories, and I want to say a little bit about what is known and techniques to understand them. But let me write down some motivating problems that, just like we've been seeing, so one recurring problem is classification of various tensor categories. So we'd like to classify some types of Hopf algebras or tensor categories. And we've been seeing that if you put some adjectives on these, then there's a lot of work and there's some hope to do some classification. So if your Hopf algebra is semi-simple, your tensor category is semi-simple, then if you understand the simple objects or modules and how their tensor products look, then you have a lot of information about what it looks like. If it's not semi-simple, then there can be very complicated ways that simple objects are put together or simple modules are put together to form all of them. So in that case, I would want to work a little bit harder to understand modules. Let me say objects. I put Hopf algebras first. Modules of Hopf algebras, or objects in tensor categories. And the problem that comes up many times is you might have an algebra of wild type or analogous notion for tensor category. You might not be able to classify all objects or modules. So you might be interested in the indecomposable objects or modules, and others are going to be put together from those. You might not be able to classify the indecomposable modules or objects. So there's a notion of wild representation type, where that's basically what it means. There's a precise notion. So what do? You can't possibly hope to understand all objects or all modules. What you might want to do is understand a little bit of sort of rough structure, how to put these objects into different boxes that they have similar flavor. And so there are various techniques to do things like that, and one of the techniques involves is going in the direction of cohomology. And so that's what I want to talk about mostly. Or maybe some techniques. For understanding involve cohomology. So let me define Hopf algebra cohomology, and cohomology for tensor category will be analogous. Okay, so I'll just let A be in Hopf algebra over a field. And I'm mostly interested in finite dimensional Hopf algebras. So here's a definition. An N extension N is a positive integer. An N extension of A modules U and V is a short exact sequence of A modules and A module homomorphisms So I'll have 0 goes to v goes to m sub n minus 1, and so on, m2, m1, u, and 0. So arrows indicate A-module homomorphisms, and the image of each one is equal to the kernel of the next one. So this is an n extension, and I want to put all n extensions together. So maybe this is just notation. So I guess I should say again, in the non-semi-simple case, this doesn't necessarily split. So there's these module homomorphisms tell you how you put these together. Okay, so notation x in A of u of b is going to be all n extensions, like so, modulo some equivalence relation. Well, it's a specific equivalence relation, but I don't want to write down too much. Just like last time, my definitions are going to be slightly vague and incomplete, but I'm happy to answer questions. Yes?
Sorry, I just missed. Are U and V themselves A modules?
Yes. Okay. U and V are A modules. That's right. Fixed 2 modules U and V, and the ones in the middle are whatever fit into a sequence of that length. Yeah, right. And then I want to consider all possible n extensions and mod out by an equivalence relation. So the equivalence relation is this. I'll describe it, but I don't want to write it on the board because this is too much. If you take 2 of these extensions, the m's in the middle might be different. The u and the v are fixed. Map u to itself identically, v to itself identically, and then if you can fill in the diagram, then those 2 are equivalent. That's not a symmetric relation if n is bigger than 1, and so extend it to an equivalence relation, and that's what you get. So you take all n extensions, mod out by this equivalence relation. This is not the standard definition of xn, but it's the shortest one. And I like to use it because it makes it easy to define a product. Okay, so this is xn of u and v. And for cohomology, Hopf algebra cohomology, I'm interested specifically in the trivial module. So I'll use the notation hn of a comma k. K is the field. I should have put that down. K is a field, and I'll define this to be xn of 2 copies of k. So we'll take the field is going to be a module under the trivial action given by the co-unit, just like before. And so I'm interested in this hn, extensions of k by k. Okay.
So where is
Yes?
the Hopf algebra structure used in this definition?
It's not. That's a good question. There's no Hopf algebra in here yet. I mean, yeah, so this makes sense for an algebra.
Yeah.
But I'm going to get to where the Hopf algebra structure comes up. Yeah, good point. Okay. Okay, so the Hopf algebra structure comes up when putting these together into a cohomology ring. I'll define next. Yeah, let me first of all write down the Uneta splice. Okay, we're going to be interested in taking 2 extensions and putting them together to get another extension. And let me just write this down for extensions of k by k. So let's take an m extension and an n extension of k by k. So for the m extension, I'll draw it this way. 0 goes to k, goes to m, and so on, down to m1 to k to 0. And for the n extension, I'll take 0 goes to k, goes to nn, and so on, down to n1 to k to 0. So I'm taking two extensions, and I want to splice them together, and that's exactly like it sounds. Okay. I'll try to do it on the board. I'm going to identify the two copies of k here. And then I have this map and this map that I can compose. Maybe I'll call this one alpha and this one beta just for the moment. So I can compose these and write this is beta composed with alpha. So then I get them out from M1 to NN. And then if you put all this together, erasing the parts in the middle, you get another extension. So 0, this gives you 0 goes to k, goes to MM, and so on down to M1 to NN via this composition. N1, k to 0. Okay, that's called the Uneda splice. And you can check that this is, again, an exact sequence, and so you get an m plus n extension. Of k by k. Okay. And that gives a product, a graded product, when you look at all of these together. So let me write down some more notation. H star of a k is defined to be the sum of all of these xn's, or hn's, however I wrote it. Hn of ak. N goes from 0 to infinity. So if I take something in hm and something in hn, those are represented by these types of extensions, and I can splice them together to get something in hm plus n. So this is a graded. Need to check that it's well defined. There's that equivalence relation, but it is. It's a graded algebra under cup product. I realize I forgot to explain what the additive structure is. Okay. So that's the multiplication. The addition is called bare sum, and that's less photogenic, so I'd rather not describe it. But there is a sum. Take two extensions of the same length, and you can add them together. There's a way to put the diagrams together. Okay, so this is a graded algebra. We still don't have a Hopf algebra. We still don't need a Hopf algebra. You can do this for any algebra. Yeah, okay, but next is the Hopf algebra. And that is, in fact, it is graded commutative. And this uses the Hopf algebra structure. Well, it uses the coproduct, the co-multiplication. That fact, because it's not true in general. It's graded commutative. Why is it graded commutative? I've just given you one possible definition. Sorry, I wrote cup product. I meant Uneda product. Okay, that I defined, but it's sometimes called cup product defined differently. There are other definitions of this product, and if you take this definition and another definition that involves a tensor product of modules, so that's where the Hopf algebra structure comes in. If you take this definition and another definition and compare the two, it turns out that one is an algebra homomorphism over the other, and that's a standard construction. There's a Hilton-Eckelmann argument that says then you have a graded commutative product. So that's where the co-multiplication comes in, the Hopf algebra structure comes in. So this is really important, right? There's a graded commutative ring, meaning it's commutative up to some negative signs, depending on the degree. Okay, so that's very important, and it will be particularly important in a minute. Let me write down the generalization. Yes?
Is that Ekman-Hilton argument going to go through for any bi-algebra? You don't need the antipode for any of that.
No, I don't believe you need the antipode. Yeah. thanks. So the antipode is useful for other things, but maybe not that. Yeah. Okay. So more generally, can do this for any tensor category. So we'll let C be a tensor category. And we can define, similarly, the cohomology with respect to the unit object 1. So defined similarly. Where's the definition? Yeah. So you have extensions of objects, and you can form the uneta splice and so on. Everything is still true in that setting. So it's graded commutative. Graded commutative ring, actually K algebra. Okay, for all the same reasons. And there's a conjecture. So you have a commutative algebra. Some nice commutative algebras are the Noetherian ones. And there is a conjecture. So this was a question, this goes back a ways. There was a question raised by Friedlander and Suslin in a paper from 1997 that I'll talk about later. And the conjecture, as I'm going to write it down, was stated by Eddinghoff and Ostrich in a paper in 2004. But many other people had wondered the same thing over the years. And the conjecture is this. Let A be a finite dimensional Hopf algebra. Okay, the statement is that the cohomology ring is finitely generated. In other words, Noetherian. In this context. Okay, that's the conjecture, and then analogous conjecture for cohomology of a finite tensor category. Finite tensor category, the cohomology is finitely generated. So I'm not going to define finite tensor category. In particular, it has finitely many simple objects, and there's some other nice properties that it have. It has enough projectives, which is sort of buried under the rug here. I'm not talking about, but they're definitely in the picture part of the other definitions that I was talking about. There's more to the conjecture. Let me just write that down. Not only is this finitely generated, but any X any two finite dimensional modules is finitely generated as a module over this cohomology ring. Okay, so what I wrote down doesn't tell you how this is going to be a module, but it is. One way to define it as a module is to recognize that this X is the same as taking its dual tensoring with the second factor and putting the unit object in the front, the trivial module in the front. And then you can form a uneta splice. So that's one way to do it. So what? Yes. That was what was known for some time. Yeah, thanks. And I'll mention that and some others that are known. Yeah. So there's an analogous statement for tensor categories. Try to squeeze it in. So So we'll use XY for objects of tensor categories. Okay, so that's a conjecture. And it is known in a number of cases. So I want to talk about where it's known and where it's not known. But maybe first let me mention some applications. So why is this important? Okay, so why do we really care about this conjecture, whether it's true or not? I mean, there may be any number of reasons. I mean, it's a Noetherian property is very important to understand if you have a ring that you're interested in. But in particular, there's a theory that is good if this is true. So there's a theory of varieties for modules, or I guess varieties for objects, that is most useful when the conjecture is true. Okay, I guess most useful is a value judgment, but so what I mean, we have, let's see, over here we have a Hopf algebra, which is often non-commutative, right? And the tensor category may have some non-commutative behavior. But you take a cohomology ring, that's commutative, graded commutative, just as good, right? You've turned your non-commutative setting into a commutative one. You've turned your objects, your modules for a non-commutative algebra into modules for a commutative algebra, graded commutative algebra. So you can use commutative algebra and algebraic geometry to study the situation. And associated to any module or associated to any object in these two settings, there will be some geometric space, some algebraic variety defined from this sort of setting. You've got a graded commutative ring and you've got a module over it for different modules for your original Hopf algebra objects in your original tensor category. So that turns out to be useful because, remember, we're looking at a non-semi-simple setting where your category or your algebra might have wild representation type. You can't hope to understand all possible modules or objects. If you're able to understand them in terms of some geometry, geometric properties will give you some information. And so this is one approach to understand properties of the modules or the objects. Okay. So maybe I should say there's been a lot of work on this going way back to finite group representations. But most recently, I wrote a paper with Peterberg, Julia Plavenik, who's here. And that's on the archive from last year. And we developed some of this theory in the setting of finite tensor categories. There's still a lot more to be done. It's just at the beginning. So maybe I should give one warning, though. This is a conjecture, and there's an analogous conjecture. For a different type of cohomology, Hochschild cohomology, for finite dimensional algebras, that's false. Okay, conjecture was that Hochschild cohomology modulo an ideal generated by nilpotent elements is always finitely generated, and that's just not true. It's graded commutative, so it has a lot of the same flavor, but that's just not true. There are known counterexamples. There are no known counterexamples to this conjecture, although if one has come up since I last heard about it. If anybody in the audience knows, please let me know. I would be happy with either a counterexample or a proof. I mean, just like to know if it's true. Yes?
Conjecture for X usually to be a module, does one of them have to be the field for any
That's a good question. The way I wrote it, it's looking like how would you get a module action? But there is a different, one of the other definitions of multiplication that I described here. In fact, maybe I can probably write this down on the board. So one of the other definitions is a tensor product. Okay. So equivalently, take a tensor product of those two extensions. So what do I mean by that? Take one of these and put it, make it vertical, right? Rotate it so it's vertical. And then take tensor product each object in this sequence with each object in that sequence, and take what's called the total complex, adding up in degrees. You add, each one of these has a degree, each one of these has a degree. For fixed degree, you add up all of the objects or all the modules, and you get a new exact sequence. So that's a second way to define the product. Have to check that everything works just fine. That's a second way to define the product, and it will use the co-multiplication. And I think what I wrote down, the module structure over there, then you can see how to get it. So you have an extension of k by k, an extension of u by v. You tensor them together. K is the unit object, and so you get another extension of u by v. Yeah. So, but there are other ways to define that as well. So, but it is a module. Okay. Okay. So we don't know if this is true. Okay. We do know it's true in a lot of settings that are important that come up. So that's what I want to talk about next. Okay, so the first set of results I want to talk about are from the 20th century. And in those days, the conjecture was known to be true in a number of settings. First one was group algebra of a finite group. And here we really want the characteristic of the field to be a prime, dividing the order of the group. Otherwise, the group algebra is semi-simple, and the cohomology is all in degree 0. There's nothing else. Yes? I'm sorry. Yeah, it's a property of the algebra, but what was the rest you said?
So if you have two co-multiplications on the same algebra, that make an algebra, then it's true for one and it's true for the other. Like, it doesn't depend on
Right. Okay. Right. Yeah. Thanks. That's a very important point. Yeah. Whether or not this is finitely generated is not using itself the co-multiplication. Right. Because there is a product for a finite dimensional algebra. Forget Hopf algebra. There's a well-defined product. That's right. So it doesn't matter which co-multiplication you're looking at. It's a statement about the algebra. Yeah.
true for this Hopf algebra, that means it's true for any algebra that is on the line.
Okay, I'm not sure I understood. What? Yes?
As an algebra, this is just k to the n.
Okay. So if the group is abelian and the characteristic of the field does not divide the order of the group, that would be true. But if the group is non-abelian and the characteristic divides the order of the group, this is not semi-simple, and it can be more complicated. Yeah. So for example, if G is Z mod P, then the group algebra is isomorphic to a quotient of a polynomial ring by a power of the generator x to the p. So it's highly non-semi-simple. And if you take a more complicated group of, say, P group, then you can get very complicated structure. Yeah. Okay, but this is really an important distinction because it really matters that what your characteristic is here. Yeah. Well, I won't write anything more down. But anyway, this has been well known for some time, and this goes back to work of Golod, three independently, Binkov and Evans, all around 1960. Okay, so that was some time ago. So this was known some time ago, and the theory of varieties for modules was developed a little bit later than that, and it's very well understood. Okay, that's the finite group case. Next was A as a restricted enveloping algebra. And again, we need positive characteristic. So restricted enveloping algebra is a quotient of an enveloping algebra that works specifically in characteristic P, and there's a definition that I don't want to write down. It will be a finite dimensional, maybe I should just say it's a finite dimensional quotient of an enveloping algebra. Universal enveloping algebra of a Lie algebra. And this is work due to Friedlander and Partial. In 1983. Okay. So those were some early results. The first sort of true Hopf algebra type result involves a non-cocommutative Hopf algebra is small quantum group. A is a small quantum group, little uq of G. And this is in characteristic 0. Where it's non-semi-simple. And this is due to Ginsburg and Kamar in 1993. And they had to put some restrictions on some of the parameters. But that was the result. So this is the case. Remember, the generators were skew primitive, right, in the sense that the co-multiplication looked sort of like a Lie algebra co-multiplication, but you had some extra group elements coming up. So that was a new type of Hopf algebra, where it's known to be true. And the next result was very general. A is any finite dimensional co-commutative Hopf algebra again, characteristic P. By co-commutative, I think I said that, but I didn't write it down. The co-multiplication is symmetric. You can switch the order of factors and get the same thing. So that's the co-commutative case. And the group algebras and the restricted enveloping algebras are both co-commutative. So 4 contains results also for 1 and 2, but not 3, which is not co-commutative. And this is due to Friedlander and Suslin in 1997. Okay, so this was a really big deal, right? All co-commutative Hopf algebras, also known as finite group schemes, viewing them a little bit different way. So this was a really big result. And like any other major news, I know exactly where I was. I remember when I heard this. I was visiting Margaret Beatty at Mount Allison University in Canada, and I was in the photocopy/coffee room refilling my cup of coffee. And Margaret came running in. There was something spewing out of the printer, you know. And she said, they proved it. They proved that the cohomology of finite-dimensional co-commutative Hopf algebra is finitely generated. She was so excited. So then we just took this huge preprint and started looking through it and discussing it. So it was a really big deal. Right. Okay, so that was last millennium. Okay. There's more to this story. But maybe I should just say, so why can't we prove it in general, right? Okay, the co-commutative case, that was great. That was a very general result. But it doesn't include the small quantum groups that we'd like to somehow capture, right, in some more general result. Why can't we prove it in general? Well, let me ask that question on the board, because it's a very important question. Okay, still open. Okay, and maybe one problem is, and that's maybe been a problem for some other questions that have come up too, is we just don't know enough yet about Hopf algebras or tensor categories, right? So we really need to know more. About the Hopf algebras or the tensor categories. Okay, so then we come back to classification efforts, right? So if we understand more about the Hopf algebras or the tensor categories, then we can use that extra information to understand more about the cohomology, and then hopefully feed back into understanding the Hopf algebras or tensor categories themselves. Okay, so let me say something about this century, or this millennium. So 21st century results. There are loads and loads. Okay, so somehow this really sparked a lot of interest, and there's been a lot of work since then. And so I'm just going to write a few names down, and if I forget anybody's name, remind me, or I apologize. But let me just give a little bit of a flavor of all of this. So Gordon in 2000 proved that this for finite quotients of quantum function algebras at roots of 1. So it was somehow analogous to the small quantum group, but a different type of algebra. In 2010, I wrote a paper with Mitya Masnak, Julia Pevsova, who will be here at MSRI for part of the program, Peter Schauenberg. And that was in 2010. Where we looked at pointed Hopf algebras with abelian group-like elements, generalizing Ginsburg and Kumar's result. We had a lot of restrictions on the parameters. The primes dividing the order of the group involved couldn't be too small. Then there was work of Bendel, Nakano, Partial, and Pillin. In 2014, where they removed some of the restrictions on parameters that Ginsburg and Kumar had. So they improved on that result by quite a lot. And so maybe I should say one thing. Some of these results are proving finite generation. Some of these results in the various papers are proving more than that. They're not only proving finite generation of the cohomology, they're giving the structure. So what does it look like? It's a null cone, for example, in some of these. A geometric flavor. So they were able to get a very specific result of that type. Okay, then I did some work with Van Nguyen in 2014, and she's here. Yes, okay. We looked at skew group algebras. So some Hopf algebras have a form of a skew group algebra. They're smash product with finite groups. And we proved some general results along those lines. Not as general as we would have liked. Chris Drupieski in 2016 proved this for finite supergroup schemes. So looking at the super case, they and Stefan in 2016 looked at the Fomin-Kirlov algebra. This is this is part of a pointed Hopf algebra with a non-abelian group of group-like elements, and that was a little bit different type of setting than the small quantum group, so that was a new type of example. Friedlander and Negron in 2018 looked at Drinfeld doubles of co-commutative Hopf algebras. So that's a construction that gives you something new, and they were able to prove the conjecture for those. And then I did some work with Ben Nguyen, Xingting Wang, in a couple of papers where we looked at positive characteristic, and in particular dimension, the cube of the characteristic or some power. There, I've got some general results as well. There's some work of Xingting Wang, also with Karen Erdmann and Oyvind Solberg on others in positive characteristic, completing the picture. And there's some recent work, well, all of this is very recent, of Chris Negron and Julia Plavnik. See her? They have some general results on finite tensor categories, some general results on duality in centers that can be very useful in some settings. Okay. So there's probably some people I've left out, but you can see there's a lot of work that's been done very recently, a lot of interest in this, and I hope that more people will become interested, because this probably is going to require a really new idea, right, to really get at the bottom of this conjecture for some types of Hopf algebras, or for all, would be nice. Okay, so I did want to say a little bit about some ongoing work of mine with Nicholas Andruszkiewicz, Ivan Andriono, and Julia Pevsova. Okay, so we've been just about finished for some time, but it's taking time to nail down the last few details and get it all written, particularly because we're not all in the same continent. So, okay, so what we're doing is we're proving the conjecture for finite dimensional pointed Hopf algebras with abelian groups of group-like elements. Okay, so they're pointed the way we've seen in several talks. All one-dimensional subcoalgebra, all simple subcoalgebras are one-dimensional, or all simple modules are one-dimensional. in this case, the subcoalgebras, the simple subcoalgebras put together form a group, and we're insisting that we have an abelian group. Non-abelian groups, that's the Wild West. Okay, non-abelian groups, where is it? The result of Ray and Stefan, they were looking at such an example. If you have a non-abelian group, you probably don't have a finite dimensional Hopf algebra to begin with. Okay, and there's a lot of work on trying to understand that as well. So I'm just looking at abelian groups. Abelian groups, the small quantum groups have abelian group of group-like elements, a lot of other examples that people are interested in, and that's really a very rich class of Hopf algebras. So this is what we're looking at. And I should say that Nicholas and Yvonne have done a lot of work on classifying these pointed Hopf algebras. And we rely very heavily on the classification results, the structure of these pointed Hopf algebras, in understanding the cohomology. So we're really using that. Okay, let me give a little bit of an idea that go into the proof, because I really want to point out how the structure, understanding the structure, is really crucial. So let me step back a little bit and talk about Jeter-Drinfeld modules. Okay, so I'll be looking at groups. A Jeter-Drinfeld module Jeter-Drinfeld module over the group algebra, KG, is a KG module, a module over the group algebra. In other words, a representation of the group with respect to that field. That is also, it's also graded. In other words, V can be written as a direct sum of vector subspaces V sub G. And the module structure and the grading behave well with respect to each other in the sense that if you take a group element H and you apply it to V sub G, you'll land in V sub HGH inverse. Okay, so if the group is abelian, then that's just saying that these are preserved under the action. These pieces are preserved. Okay, so that's a Jeter-Drinfeld module. And if I have a Jeter-Drinfeld module, and I'll give you a few in a minute, I can put that together, and I will be coming back to the pointed Hopf algebras, but this is, I want to go backwards and start with something else. And I'll come to the pointed Hopf algebras in a minute. Okay, so suppose I have a Jeter-Drinfeld module, then it's a fact that the tensor algebra on V is a braided Hopf algebra. Braided Hopf algebra. And saying this a different way, in other words, it's a Hopf algebra in the category of Jeter-Drinfeld modules which I meant to write down the notation. So the notation KG superscript KG subscript YD is a category of all such. And if you start to write it down, there's a notion of morphism that makes sense and so on. This also this notion in the finite dimensional case corresponds to a Drenfeld double, modules for Drenfeld double. So this is, if you're familiar with that, these are similar notions, equivalent notions. Okay, so Hopf algebra in this category. So it's Hopf algebra, I mean, there's co-multiplication, co-unit, as well as multiplication unit. There's an antipode. All of these are morphisms in the category. So that's the setting. A Hopf algebra that I defined before is a Hopf algebra in a category of vector spaces. So we're asking just something a little bit different here. Anyway, it has that structure. And there's another fact. There is a largest. I'm just skimming some of the ideas to give a big picture. So it turns out that there's a largest ideal, we call it J, of the tensor algebra that's contained, well, generated in degree 2 or higher, that is also a co-ideal. And by that I mean the co-multiplication takes J to J tensor the whole algebra, tensor algebra, plus the tensor algebra tensor J. So this is the dual notion to an ideal of an algebra. And I'll define, there are many other ways to define it. This just seemed like the shortest for today. Nichols algebra is T of V mod J. So it's an algebra that has generators given by a vector space basis, the vector space we started out, and there's some universal construction here. So let me just give an example, a couple of examples that will also tie it back into where we're going to use it. Okay, Nichols algebra. These turn up in a lot of places. So a small example is this one. Let's take little UQSL2, small quantum group, and I want to, let me look at a subalgebra, put a plus there. I just want to take the part generated by one of those nilpotent generators E. So E to the n is 0. This is in the case where Q is an nth root of unity. Let's say primitive nth root of unity. So that the small quantum group, we have a definition. This is a Nichols algebra. Okay, you need to take a particular vector space. Okay. The group is going to be a group of order n, acting on it by multiplying by Q. But that's a Nichols algebra, so that's an example. Polynomial ring is also a Nichols algebra for a different action. So that's a very small example, but it's relevant because, in fact, this extends all of the small quantum groups. If you look at sort of the positive part, that's going to be a Nichols algebra. Okay. So Nichols algebra is underlying a lot of this. UQ SL2, if you make this a little bit bigger, sometimes written greater than or equal to 0, you throw in the group-like elements. So this is the algebra generated by E and K, subject to relations En equals 0, K to the n equals 1, and Ke equals Q squared Ek, or some slight variation on this, depending on where you're looking. This is isomorphic to UQSL2 plus smash product with the group generated by K. I may have written this down before, maybe slightly differently, right? So this is also called, the smash product is also called, in this context, Bosanization of the Nichols algebra UQSL2 plus. So in other words, we have a Nichols algebra. There's associated to it some group. Right, it's coming from a Jeter-Drenfeld module. And if you can, the group is acting on it, and so you can form this smash product. Okay, that's Bosanization. All right, so let me write down UQSL2 itself, you've got one more generator, right? And that turns out to be the Drinfeld double of this modulo some group-like elements. More generally, this example is very typical, although in general, relations are much more complicated, but this still gives you the picture. So more generally, what happens? Finite dimensional pointed Hopf algebras. Finite dimensional pointed Hopf algebras with abelian group of group-like elements are exactly co-cycle deformations of bosonizations of Nichols algebras. Okay, so in other words, they look exactly like, well, okay, they look sort of like this. You have a Nichols algebra that's defined somehow in some universal way. You take the bosonization, meaning you smash with a group algebra. And then there's a co-cycle deformation. So there's a precise definition of that that will give you your pointed Hopf algebra. So they all come from this type of construction. And really, the most important thing to understand first is the Nichols algebra. So in order to prove finite generation of cohomology, we want to understand cohomology of Nichols algebras. Okay. And their structure is governed by Dynkin diagrams and related diagrams in the classification that several people have worked on, including Nicholas and Ivan. And then we need to understand their bosonizations, their deformations, and so on. I think I probably needed to mention somewhere that we are working in characteristic 0, not to claim too much here, because the positive characteristic case is much, much more involved, and we haven't looked at that yet. So I think I'll stop here. Thank you. Okay, yes.
Is it known that the conjecture is stable under co-cycle deformation? It is known for a Hopf algebra and you take a
Co-cycle deformation. So that's a good question. So we handled co-cycle deformations through a Drinfeld double construction. So I'm not sure if that statement is known to be true the way you would hope, but I have to think about that. Maybe ask Nicholas. He would remember the latest. Another question? Yeah.
So in the group, do you handle this case by case? Like you have all these cases for Nichols algebra?
Yeah. Yeah, we handle it case by case. This is why it would be good to have a better proof, right? We've got the type A, type B, type C, and all the different possibilities case by case. The Nichols algebra has a particular structure, and we handle that, and yeah. UFO, yes, there are UFOs. Those are the ones that are not coming from Dynkin diagrams in some way. Yeah, it's a lot to. Yeah. Last I looked, it was 130 pages. So I don't know. Yes.
Suppose your Hopf algebra has additional structure, say it's quasi-triangular or quasi-triangular. Going to get it very quick. How does this structure translate to cohomology?
Yeah, okay, that's a very good question. If you have a quasi-triangular Hopf algebra, do you have more information about the cohomology? That's a good question. I think there are people in this room who have looked at that, particularly if the Drinfeld doubles. There's some things that are known for Drinfeld doubles, which are quasi-triangular. So there is something, but I'm not sure about a general statement. But, okay. Another question. Why is it called bosonization? Someone in this room may be able to answer this better than I. I'm just... Susan's not here.
She has some thoughts.
The Radford byproduct is what she thinks it should be called.
We should call it the Radford. We should call it the Radford byproduct. Okay, somehow this just stuck. So, yeah. Yeah. Another question?
So when you do this proof here and you use the cases, you really check the structure of the homology or just prove the conjecture?
Okay, that's a good question. We do not work out the structure of the cohomology. We prove the conjecture. We work out part of the structure in that we really need to understand some of the even degree part of it very well, because that's what's really governing the finite generation. But we don't understand all the structure of cohomology.